Module 4, that is complex variable, differentiability, and the topics are function of complex variable, limits and continuity of a function, analytic function, and example based on the topics which are shown at first, second and third position. Yeah, so very first we have to start with the complex variables. Right, so you must have heard about the complex numbers. Those were nothing but the combination of the real numbers written in this manner, a plus minus iota b, where a and b were real numbers. Right, a and b were real numbers. Okay, so this combination is known as complex number. But here we are talking about the complex variable. Okay, so complex variable is nothing but if we have taken x and y as variables in place of a and b, then z is the combination of x plus iota y or minus iota y. Right, so this z is having two variables simultaneously, x and y. So this is known as complex variable. Alright, so if we talk about the function of complex variable, so that would be written as f of z, and if we take this function as w, then we can call this w as function of complex variable z. Right? Okay, so here x and y are called real and imaginary parts of z, and of course we can write this z in the polar form as r e raised to the power iota theta. If we put x is equal to r cos theta and y is equal to r sin theta, then the combination z becomes r times cos theta plus iota sine theta. So this is further written as r e raised to the power iota theta. So this is also depending upon r and theta, right? So this we have understood about the complex variable and function of complex variable. Alright, so we can understand through this graph as well. Here in xy plane, if we talk about the complex variable or complex numbers, then this plane is known as Argand plane or complex plane. So here we can denote the point in terms of x and y. So z becomes x plus iota y, and if it is written in terms of r and theta, so this OP magnitude is small r and theta is the inclination. Okay. Function of complex variables. Here I have already told you in the previous slide that if we consider any function of complex variable z, then we can write this w as f of z. Where we can write this w as, since it is a function of complex variable, so it can be written as u plus iota v, where u and v both are functions of x and y. Right, u and v both are functions of x and y. So we can write this w as the combination of real and imaginary part. Limit of a function. Limit of a function is, let fz be a single valued function defined at all points. Then single valued function means, what is the meaning of single valued function actually? So single valued function means for single value of z, fz should have single value. Or in other words, we can also say that for unique value of z, fz should have unique value. That is known as single valued function. Defined at all points means nowhere we are getting point of singularity. So this mathematically can be denoted by this limit z tends to z naught. Z naught is some point. Fz is equal to L, which is some finite number. So then we say that limit of this function fz exists. right? And limit of function should exist. But one point is, in addition to this, that limit must be existing in the independent manner. Independent manner means, since we know that z is a complex number, so it is depending upon x and y both. X and y both. So of course z would be tending to z naught. Z would be tending to z naught following some path. So, and that path would be what? Some y as function of x. So this may be any path. So whatever the path is followed to take this z tends to z naught, this limit should be unique. It should not change. Then we call that limit z tending to z naught if z is equal to L, which is unique. Then the limit of this function of z exists. Right, so this point is to be remembered, that limit should be independent of the path or in manner the manner in which z is approaching to z naught. I hope this point will be clear. If we get two different limits as z tends to z naught along two different paths, then limit does not exist. I hope this point is clear to you all. Next is continuity. So in lower classes we had heard about the continuity. There we had studied that left hand limit should be equal to right hand limit should be equal to the value of the function at that particular point at which we are finding out the or taking out the continuity. Right, so here function fz of a complex variable z is said to be continuous at the point z naught if limit z tends to z naught if z is equal to fz naught. So this is the condition for fz to be continuous. Differentiability. So of course, if a function of complex variable fz is continuous, then it would be differentiable at that point of continuity. Let's understand in a detailed manner. Let fz be a single valued function of variable z, then f dash is equal to f dash z is equal to limit delta z tends to 0 fz plus delta z minus fz over delta z. This is nothing but the formula for the first principle, derivative through first principle. You all must have seen this formula earlier. So this is the basic definition of differentiability. Provided the limit exists and it is independent of path along which delta z is tending to 0. As I have told you in the previous slide, that delta z will tend to 0 or z will tend to z naught following some path, and that path would be nothing but the y depending upon x in any manner. So this path may be of any shape, any function can be the path by taking this delta z tends to 0 or z tends to z naught. Right, so if we follow more than one path, of course we would be following, then this limit should be unique. So if it is unique, then we call that it is independent of path. Right, so this is the definition. These are the definitions of continuity and differentiability for the function of complex variable. All these points, small points and conditions should be remembered. Right. So here, if we have taken 2 points, P and Q, since this delta z is very small, we already are aware about this. Delta z is also known as small h, where h was tending to 0. So here we can reach from P to Q following any path. So here some path are shown, this to this, then this. Yeah, this path PR, then RQ. Here if I write this as S, then PS, then SQ, and if I follow this path, I can follow this straight line, I can follow this path. So many paths can be followed, and an infinite number of paths can be followed from reaching from P to Q. Right. So mathematically, when we solve questions, then we can show this thing by following 2 or 3 paths. Right. Maximum 2 or 3 paths. We can find out the value of f dash z through this definition, and it should be unique. Means the value of f dash z, whatever be the point at which we are evaluating or finding out, that should be same. So if it is unique, then we can see that the function is differentiable at that point. The same condition is for continuity. Right, next is analytic function. About analytic function, I had explained you in first semester as well that any function which is defined in some domain or interval, that should exist at each and every point of that domain. Means no point should be there at which function ceases to exist. Ceases to be exist. Right, so that is known as analytic function. So here just have a look. Function is said to be analytic at a point z0 if f is differentiable not only at z0 but at every point of the some neighborhood of the point z0. Right, so that is known as analytic function. Okay, entire function, a function which is analytic everywhere, is known as entire function. All right, so if I show you, suppose we have this point z0 here, right, and its neighborhood, assuming this point as center, if we draw a very small circle, then all the points which are lying within this neighborhood, the function should satisfy, the function should have the value, finite value I would say, at all these small points which are lying in this neighborhood. Means in the neighborhood of z0 or all the points lying inside this small circle of radius very small, the function should be existing or having finite value. Then we would say that that particular function is analytic at point z0. Right? So this was the mathematical notation explanation for an analytic function. Entire function I have already told you. Function which is analytic everywhere is known as entire function. Everywhere means that in the interval or in the domain where it is defined. So a function which is defined in any interval, it should be analytic at each and every point of that interval. Then that is known as entire function. Okay, and now necessary condition for the function fz to be analytic is that for fz is equal to u plus iota v to be analytic at all the points in region capital R, ux is equal to vy. These are nothing but the partial derivatives, and uy is equal to minus vx, provided all the partial derivatives of u and v exist. This is nothing but ux. In short, we have been writing like this. Ux, this is uy, this is vx, and this is vy. So if all the partial derivatives exist of u and v, then ux is equal to vy and uy is equal to minus vx. Remember this condition? This is the necessary condition for function fz to be analytic. Right. And these are known as Cauchy-Riemann equations. Right. So these conditions, ux is equal to vy and uy is equal to minus vx, are known as Cauchy-Riemann or CR equations. Cauchy-Riemann equations or CR equations. Now let's have a look at sufficient condition for a function fz to be analytic. The sufficient condition for fz is equal to u plus iota v to be analytic at all points in a region capital R are ux is equal to vy and uy is equal to minus vx. This is necessary condition, but sufficient condition is this, that all the partial derivatives are continuous functions of x and y in region R. So this condition will show that f dash z exists uniquely. So this is the sufficient condition. Uniquely means derivative is independent of path. Derivative is having unique value. So this is sufficient condition that f dash z exists uniquely. Cauchy-Riemann equation in Cartesian coordinates, we have already seen that ux is equal to vy and uy is equal to minus vx. Right. So this I have already told you that CR equations are necessary condition but not sufficient for an analytic function. CR conditions are sufficient if partial derivatives are continuous. So that means sufficient condition is what? All the partial derivatives are continuous, shows that derivative exists uniquely. So this point you have to remember. Let's understand through a question. Show that the function e raised to the power x cos y plus iota sin y is an analytic function and find its derivative. So our function is this. So we'll compare it with u plus iota v, where u and v both are the functions of x and y. So here u would be e raised to the power x cos y and v is this. So what we have to do, we have to find out Cauchy-Riemann equation and those conditions should hold and its derivative should exist uniquely, independent of part, right? So both the conditions we have to check here. So very first we will check for Cauchy-Riemann equation. So that's why we have differentiated this u partially with respect to x. We are getting this value and v, y. So e raised to the power x cos y both are same, as you can see here that ux is coming out to be same as vy. And here u is further differentiated partially with respect to y, so that's why we are getting this result. And this v is further differentiated partially with respect to x, we are getting this result. So from here we can conclude that uy is equal to minus v x. So these are the Cauchy-Riemann equation or CR equation which are satisfied here. Right. So this necessary condition